Multi-Cloud Network Hub Comparison. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today's presentation focuses on a critical comparison in the cloud networking space. Google Cloud Platform's Network Connectivity Center, AWS's Transit Gateway, and Microsoft Azure's Virtual WAN. These three services represent the pinnacle of hub-and-spoke networking architectures in their respective cloud ecosystems, and understanding their differences is essential for any multi-cloud strategy. Each platform has taken a unique approach to solving the same fundamental problem. How do you efficiently connect multiple networks, whether they're cloud-based VPCs, on-premises data centers, or remote branch offices, in a scalable and manageable way? The hub-and-spoke model is the cornerstone of modern cloud networking architecture. In this design pattern, a central hub acts as the traffic aggregation point, and multiple spokes, representing different networks, connect to this hub. This architecture eliminates the need for complex mesh topologies where every network must be directly connected to every other network. Instead, all traffic flows through the central hub, which provides routing, security policy enforcement, and traffic inspection capabilities. This design dramatically simplifies network management, reduces the number of connections you need to maintain, and provides a single point of control for network policies. Google's Network Connectivity Center represents their vision of a software-defined networking hub that embraces multi-cloud and hybrid connectivity. AWS Transit Gateway has been the industry standard for several years, providing high-throughput, scalable inter-VPC and VPN connectivity. Azure Virtual WAN brings Microsoft's enterprise networking expertise to the cloud with deep integration into their SD-WAN ecosystem. Each solution has distinct strengths, licensing models, routing capabilities, and operational characteristics that make them suitable for different use cases. Throughout this presentation, we'll examine these differences in detail, exploring how each platform handles routing domains, spoke attachment methods, multi-cloud integration, and SD-WAN connectivity. Hub and spoke architecture fundamentals. The hub-and-spoke topology is perhaps the most important concept to understand in modern cloud networking, because it fundamentally changes how we think about network connectivity at scale. In traditional networking, when you had multiple sites or networks that needed to communicate, you would often create point-to-point connections between each pair of sites. This mesh topology works fine for a small number of sites, but the complexity grows exponentially as you add more locations. With just 10 sites, you would need 45 separate connections to create a full mesh. With 20 sites, you need 190 connections. This becomes completely unmanageable from both a configuration and cost perspective. The hub-and-spoke model solves this scaling problem by introducing a central aggregation point. Instead of connecting every spoke to every other spoke, each spoke only needs one connection to the hub. The hub then handles all the routing between spokes. This reduces the number of connections from n factorial in a mesh topology to just n connections in a hub and spoke topology, where n is the number of spokes. For our 20-site example, instead of needing 190 connections, you only need 20 connections. This dramatic reduction in complexity is why hub and spoke has become the dominant architecture pattern in cloud networking. In the context of cloud platforms, the hub is typically a managed service provided by the cloud vendor. For GCP, this is the Network Connectivity Center hub. For AWS, it's the Transit Gateway. For Azure, it's the Virtual WAN hub. These managed hubs provide not just basic routing functionality, but also advanced features like route filtering, traffic inspection integration, firewall rule enforcement, and connectivity to on-premises networks through VPN or dedicated connections. The spokes can be various types of networks: cloud VPCs or VNets, on-premises data centers connected via VPN or dedicated interconnects, remote branch offices using SD-WAN appliances, or even networks in other cloud providers for multi-cloud architectures. One of the key architectural decisions in hub and spoke design is whether to use a single regional hub or multiple regional hubs. A single hub simplifies management and provides a single point of control, but it can become a bottleneck and a single point of failure. Multiple regional hubs provide better performance by keeping traffic close to its source and destination, and they improve resilience by eliminating single points of failure. However, they add complexity because you now need to manage routing between hubs. Each cloud platform handles this trade-off differently, with varying levels of support for multi-hub architectures and inter-hub routing. GCP Network Connectivity Center Architecture. Google Cloud's Network Connectivity Center, often abbreviated as NCC, represents Google's approach to unified network management across hybrid and multi-cloud environments. NCC was designed with a software-defined networking philosophy at its core, emphasizing flexibility and programmatic control. Unlike AWS Transit Gateway, which launched as a regional service for VPC interconnection, NCC was built from the ground up to be global and hybrid first. This means that an NCC hub is not bound to a single region. Instead, it's a global construct that can aggregate connectivity from resources across all GCP regions and even from other cloud providers or on-premises networks. The fundamental building block in NCC is the hub resource. When you create an NCC hub, you are essentially creating a global routing domain that can span your entire network infrastructure. This hub does not have a specific regional location. It exists as a logical entity in Google's control plane. You then attach various types of spokes to this hub, and these spokes can be located in any region. This global nature of NCC is particularly powerful for organizations with worldwide operations, because it means you do not need to create separate regional hubs and figure out how to interconnect them. All your routing happens within a single global hub construct. NCC supports several types of spoke attachments, each serving different connectivity needs. VPC spokes are the most straightforward type. These attach VPC networks directly to the NCC hub, enabling communication between VPCs in the same project or across different projects. Router appliance spokes are particularly interesting because they allow you to attach third-party network virtual appliances, for example SD-WAN controllers, firewalls, or routing platforms, to the NCC hub. This enables integration with existing network architectures and allows you to leverage specialized networking functions. VPN spokes connect on-premises sites or remote offices through Cloud VPN, either using classic VPN or the more modern high-availability VPN with BGP routing. Finally, VLAN attachment spokes provide connectivity through Cloud Interconnect, Google's dedicated connection service for high bandwidth, low-latency connectivity to on-premises infrastructure. One of NCC's most powerful features is its support for data plane processing within the hub. Unlike some hub and spoke implementations where the hub is purely a control plane construct for route exchange, NCC can actually process and forward data traffic through the hub. This is particularly useful for scenarios where you need to insert network functions, like firewalls or intrusion detection systems, into the data path. You can deploy network virtual appliances in GCP and configure them as router appliance spokes, and then route traffic through these appliances for inspection and policy enforcement. This gives you the flexibility to implement complex security architectures while maintaining the simplicity of a centralized hub and spoke topology. Let's examine the GCP commands shown in the slide in detail. The first command uses gcloud network connectivity hubs create, which is the gcloud CLI command for creating a new network connectivity center hub. The myGlobalHub parameter is the name you are assigning to this hub. You will reference it in subsequent commands. The description flag with the value Global Connectivity Hub provides human-readable documentation about the hub's purpose. This description appears in the Cloud Console and helps team members understand what this hub is used for. This command creates the global hub resource in Google's control plane, and it returns immediately because the hub is a logical construct rather than physical infrastructure that needs to be provisioned. The second command, gcloud network connectivity spokes link VPC network creates a VPC spoke attachment. Let's break down each parameter. The VPC spoke 1 parameter is the name you are assigning to this spoke resource. The hub parameter with value my global hub references the hub we just created, establishing the relationship between this spoke and that hub. The VPC network parameter specifies the full resource path to the VPC you want to attach. The format project/my project/global/networks/VPC1 follows GCP's resource naming convention where you specify the project ID, the scope which is global for VPC networks, and the network name. This full path is necessary because GCP resources can exist across multiple projects, and this ensures you are referencing exactly the right VPC. The region parameter US Central 1 indicates where this spoke attachment should be active. Even though the hub is global, spoke attachments can be regional, allowing you to control which regions participate in the hub's routing domain. Notice there is no subnet specification required, unlike AWS Transit Gateway, because NCC attaches at the VPC network level rather than requiring specific subnets. AWS Transit Gateway Architecture. AWS Transit Gateway, commonly referred to as TGW, was Amazon's answer to the growing complexity of VPC interconnection and hybrid cloud networking. Before Transit Gateway, connecting multiple VPCs required either VPC peering connections, which created a mesh topology that did not scale well, or complex VPN hub architectures using EC2 instances, which were difficult to manage and had limited throughput. Transit Gateway fundamentally changed this by providing a managed, highly scalable regional hub that could connect tens of thousands of VPCs and VPN connections with minimal configuration overhead and high throughput. The architecture of Transit Gateway is centered around the concept of a regional hub. When you create a Transit Gateway, it exists within a single AWS region and can connect to VPCs and VPN connections within that region. Unlike NCC's global hub model, each Transit Gateway is regional, which means that for a multi-region deployment, you need to create separate Transit Gateways in each region and then connect them using Transit Gateway peering connections. This regional model aligns with AWS's overall architecture philosophy where most services are regional by default, and it has both advantages and trade-offs that we will explore throughout this presentation. Transit Gateway introduces the concept of route tables, which are distinct from the route tables you use within VPCs. A Transit Gateway route table determines how traffic is forwarded between the different attachments connected to the Transit Gateway. You can create multiple route tables within a single Transit Gateway, and each attachment can be associated with a specific route table. This enables powerful segmentation scenarios where you can control which attachments can communicate with which other attachments. For example, you might create a production route table that only allows communication between production VPCs, and a separate development route table for development VPCs, all within the same Transit Gateway. Attachments are how you connect resources to a Transit Gateway. The most common attachment type is a VPC attachment, which connects a VPC to the Transit Gateway by creating ENIs in specified subnets within the VPC. VPN attachments connect on-premises sites through IPsec VPNs with BGP routing support. Direct Connect Gateway attachments enable connectivity through AWS Direct Connect, Amazon's dedicated connection service. Transit Gateway Connect attachments are a newer addition that supports GRE tunnels and is particularly useful for SD-WAN integrations. Finally, peering attachments connect two Transit Gateways together, either in the same region or across different regions, enabling multi-region connectivity. Now let us examine the AWS commands in detail. The first command, AWS EC2 Create Transit Gateway, creates a new Transit Gateway resource in your current AWS region. The description parameter Production Transit Gateway provides human-readable documentation for this resource. The options parameter is particularly important as it contains configuration settings that determine how the transit gateway behaves. Let us break down the options. Amazon side ASN equals 64512 sets the autonomous system number that AWS will use for BGP routing. This is in the private ASN range from 64512 to 65534, which is reserved for private use and will not conflict with public internet routing. You might choose a specific ASN to match your existing on-premises network's ASN scheme. The default route table association equals disable is a critical setting that prevents attachments from being automatically associated with a default route table. This gives you explicit control over routing, which is essential for implementing proper network segmentation. If you left this enabled, all attachments would automatically be able to route to each other, which might not meet your security requirements. The second command, AWS EC2 create transit gateway VPC attachment, attaches a VPC to the transit gateway we just created. The transit gateway ID parameter uses the identifier TGW- beginning with 01 ending with F0, which would have been returned from the create transit gateway command. In practice, you would capture this output or look it up before running the attachment command. The VPC ID parameter VPC- beginning with 0 ending with 90 specifies which VPC you are attaching. The subnet ID's parameter is crucial and unique to AWS's transit gateway model. You must provide a space-separated list of subnet identifiers, and you should specify one subnet from each availability zone where you want the transit gateway to be available. In this example, we are providing subnet- beginning with 01 ending with BC and subnet- beginning with 45 ending with EF, which would typically be in two different availability zones. Transit Gateway will create elastic network interfaces in these subnets, and these ENIs are the actual connection points. The subnets you specify should be dedicated to Transit Gateway usage and do not need to be large. A /28 subnet providing 16 IP addresses is typically sufficient. When traffic from your VPC needs to go to the transit gateway, your VPC route tables will direct it to these attachment subnets, where the ENIs receive the traffic and forward it into the transit gateway for routing to the destination. Azure Virtual WAN Architecture. Azure Virtual WAN, abbreviated as VWAN, represents Microsoft's comprehensive approach to building large-scale hub-and-spoke networks in the cloud. What distinguishes Virtual WAN from other hub-and-spoke solutions is its deep integration with the SD-WAN ecosystem and its focus on branch connectivity. Microsoft designed Virtual WAN with the enterprise WAN use case as the primary driver, which means it excels at connecting large numbers of branch offices and remote sites to Azure resources and to each other. This SD-WAN focus is evident in the platform's native support for multiple SD-WAN vendor appliances and its simplified branch connectivity workflows. The Virtual WAN architecture consists of two main components: the Virtual WAN resource itself, which is a global construct, and one or more Virtual WAN hubs, which are regional. This hybrid global-regional model combines aspects of both NCC's global approach and Transit Gateway's regional approach. The Virtual WAN resource acts as a container and provides a single management plane for all your hubs and connections, while the individual hubs are deployed in specific Azure regions and handle the actual traffic forwarding within those regions. This design allows you to maintain a unified view of your network while still benefiting from regional traffic optimization. Virtual WAN hubs come in two SKU tiers, Basic and Standard. The Basic SKU supports only site-to-site VPN connections and is suitable for simple branch connectivity scenarios. The Standard SKU, which is what most organizations use in production, supports ExpressRoute, point-to-site VPN, site-to-site VPN, VNet connections, and inter-hub routing. The Standard SKU also enables advanced features like Azure Firewall integration, custom route tables, and routing intent policies. This tiered approach allows organizations to start simple and scale up as their needs grow. One of Virtual WAN's most powerful features is its concept of routing intent. Routing intent is a declarative policy that specifies what types of traffic should be routed through Azure Firewall or other network virtual appliances deployed in the hub. Instead of manually configuring complex routing rules, you simply declare your intent, such as route all internet-bound traffic through the firewall, or route all private traffic through the network virtual appliance, and Virtual WAN automatically configures the necessary routing and security policies to implement this intent. This abstraction significantly simplifies security architecture design and reduces the chance of misconfigurations that could create security gaps. Let's examine the Azure CLI commands in detail. The first command, AZ network vWAN creates the Virtual WAN resource itself, which serves as the global container for all your hubs and connections. The name parameter myVirtualWAN is the identifier you will use to reference this virtual WAN in subsequent commands. The resource group parameter myResourceGroup specifies which Azure resource group will contain this resource. Resource groups in Azure are logical containers that group related resources together for management, billing, and access control purposes. You would have created this resource group beforehand using AZ group create. The type parameter standard is critical because it determines which features are available. The standard type gives you access to all virtual WAN capabilities, including express route, multiple VPN types, VNet connections, inter-hub routing, and advanced features like Azure Firewall integration. If you only needed basic site-to-site VPN connectivity and wanted to minimize costs, you could use Basic instead. But Standard is recommended for production deployments because it provides the flexibility to add features as your needs evolve. The second command, AZ network vHub creates a regional virtual WAN hub within the virtual WAN we just created. The name parameter East US Hub identifies this specific hub. The resource group parameter myResourceGroup is the same resource group that contains the virtual WAN. It's good practice to keep related resources in the same resource group. The vWAN parameter myVirtualWAN references the virtual WAN resource we created in the first command, establishing the parent-child relationship. This is how Azure knows this hub belongs to that virtual WAN. The address prefix parameter 10.0.0.0/24 is critical and deserves careful attention. This specifies the IP address range that the hub itself will use for its internal infrastructure. This is not the address space of your VNets. Rather, it's the address space used by the hub's routing infrastructure, VPN gateways, express route gateways, and other hub services. This address prefix must be a /24 or smaller CIDR block, and it absolutely must not overlap with any of your VNet address spaces, your on-premises networks, or other hub address prefixes. If there's overlap, routing will fail. The location parameter East US specifies which Azure region this hub will be deployed in. This determines the physical location of the hub's infrastructure and affects which VNets and connections can be attached with optimal performance. You would typically create hubs in regions where you have significant VNet presence or where your branch offices are geographically located. Routing domain concepts across platforms. Routing domains are a critical concept for understanding how these hub and spoke platforms enable network segmentation and traffic isolation. A routing domain is essentially a collection of routes that determines how traffic is forwarded between different parts of your network. By creating multiple routing domains, you can implement sophisticated traffic patterns where some networks can communicate with each other while others remain isolated, all within the same physical hub infrastructure. This is crucial for implementing security boundaries, separating production and development environments, or meeting compliance requirements that mandate network segregation. In GCP's Network Connectivity Center, routing domains are implemented through the concept of spoke groups and routing configurations. NCC uses Border Gateway Protocol extensively for route exchange between spokes and the hub. When you attach a spoke to an NCC hub, you configure which routes should be advertised to the hub and which routes should be learned from the hub. This gives you fine-grained control over route propagation. You can use route filters to implement routing domains by controlling which spokes receive which routes. For example, you might configure your production VPC spokes to only receive routes for other production resources, while your development spokes receive a different set of routes. AWS Transit Gateway implements routing domains explicitly through Transit Gateway route tables. Each route table represents a routing domain, and you can create multiple route tables within a single transit gateway. When you attach a VPC or VPN to the transit gateway, you associate that attachment with a specific route table. The route table determines which destinations the attachment can reach. You populate these route tables either through static routes that you configure manually or through dynamic route propagation from VPN attachments using BGP. The power of this model is that you can create complex network topologies where different sets of VPCs have different connectivity patterns, all managed through route table associations and propagations. Azure Virtual WAN takes a more automated approach with its routing tables and routing intent features. In Virtual WAN, each hub has a default route table that all connections use by default. You can also create custom route tables for more complex routing scenarios. What makes Virtual WAN's approach unique is the routing intent feature, which allows you to declaratively specify routing policies without manually managing route entries. For example, you can specify that all internet-bound traffic should route through Azure Firewall, and Virtual WAN automatically creates the necessary route entries in all the relevant route tables. This automation reduces operational complexity, but it requires understanding how the automatic route creation works to avoid unexpected traffic patterns. VPC and VNet spoke attachment methods. Attaching virtual networks to your hub is the most fundamental operation in hub and spoke networking, and each platform has developed its own approach to this process. Understanding these attachment methods is crucial because they determine not only how you configure the connectivity but also how traffic flows, what IP addressing requirements you have, and what operational characteristics you can expect. The attachment mechanism also affects important aspects like bandwidth limits, latency, and cost, so choosing the right attachment method for your use case is an important architectural decision. In GCP's Network Connectivity Center, VPC spoke attachments are created by defining a spoke resource that references a VPC network. The attachment process is relatively straightforward. You specify the VPC network you want to attach, configure the regions where the attachment should be active, and define routing parameters such as which routes to advertise and which to accept from the hub. NCC uses Google's global network backbone to carry traffic between VPCs attached to the same hub, which means you get Google's high-performance global network infrastructure for inter-VPC communication. One important characteristic of NCC is that it does not require any special subnets or IP address reservations within your VPCs for the hub connectivity. The connection is handled at the network level rather than through subnet attachments. AWS Transit Gateway takes a different approach with its VPC attachments. When you attach a VPC to a transit gateway, you must specify one or more subnets in each availability zone where you want the attachment to be available. Transit Gateway then creates elastic network interfaces in these subnets, and these interfaces are the actual connection points between your VPC and the transit gateway. This subnet-based attachment model has several implications. First, you need to plan for these attachment subnets in your VPC CIDR design. They don't need to be large. Typically just a /28 subnet is sufficient, but they do need to exist. Second, traffic from your VPC to the transit gateway is routed through these attachment subnets, so you need to ensure your route tables properly direct traffic to the transit gateway. Azure Virtual WAN's VNet connections are conceptually simpler than AWS's subnet-based approach. When you connect a VNet to a virtual WAN hub, the connection is made at the VNet level rather than requiring specific subnets. Azure creates the necessary infrastructure in the hub to forward traffic to and from the VNet. One unique aspect of virtual WAN VNet connections is the concept of associated and propagated route tables. When you create a VNet connection, you associate it with a route table, which determines which routes the VNet will use to reach destinations. You also configure which route tables the VNet connection should propagate its routes to, which determines which other connections will learn routes to this VNet. This association and propagation model provides flexibility in implementing routing domains while maintaining a simpler connection model than a WSS subnet-based approach. Let's break down the commands shown for each platform. The GCP command, gcloud network connectivity spokes link VPC network create prod VPC spoke, creates a VPC spoke at the network level. The prod VPC spoke parameter is the name for this spoke resource, which you will use to reference it later. The hub parameter myHub references the NCC hub we want to attach to, establishing the parent-child relationship. The VPC network parameter specifies the full resource path to the VPC using GCP's standard resource naming format. project/myproject/global/networks/prod VPC. This format includes the project ID which owns the VPC, the scope which is global for VPC networks, and the network name. This full path is necessary because you might be attaching VPCs from different projects to the same hub, and this ensures you are referencing exactly the right VPC. Notice there is no subnet specification here because NCC attaches at the VPC network level, simplifying the configuration and eliminating the need to plan for dedicated attachment subnets. The AWS command, AWS EC2 create transit gateway VPC attachment, requires more parameters because of its subnet-based model. The transit gateway ID parameter TGW123 identifies which transit gateway to attach to. This would be the ID returned when you created the transit gateway. The VPC ID parameter VPC456 specifies the VPC you are attaching. The subnet ID's parameter is critical and unique to AWS. It takes a space-separated list of subnet identifiers. You should provide subnet ABC and subnet DEF, which represent subnets in different availability zones. Transit Gateway will create ENIs in these subnets. These subnets should be dedicated to transit gateway use and should be small. Typically, just a /28, providing 16 IP addresses, is sufficient. The key point is that you must pre-plan these subnets in your VPC CIDR design. When you want to route traffic from your VPC to the transit gateway, your VPC route tables will have entries directing traffic to the transit gateway, and AWS will automatically route that traffic through the ENIs in these attachment subnets. The Azure command, AZ network VNet hub connection creates a VNet connection to a virtual WAN hub. The name parameter prod VNet connection identifies this connection. The remote VNet parameter specifies the full resource ID of the VNet you are connecting. In Azure, resource IDs follow the format /subscription/subscription ID/resource groups/resource groups/providers/Microsoft.network/virtual networks/VNet name. This format ensures the correct VNet is identified even if you have VNets with the same name in different resource groups or subscriptions. The VNet hub name parameter myHub identifies which virtual WAN hub this connection attaches to. Azure handles all the networking details automatically without requiring you to specify subnets. The connection is made at the VNet level, and Azure creates the necessary routing infrastructure in the hub to forward traffic to and from this VNet. This simplicity is one of virtual WAN's strengths, reducing the configuration burden on administrators. VPN and interconnect connectivity options. Connecting on-premises networks and remote sites to your cloud hub is a critical requirement for hybrid cloud architectures. All three platforms provide both VPN-based connectivity for encrypted connections over the internet and dedicated connection services for high bandwidth, low latency connections through private connections. The choice between VPN and dedicated connections involves trade-offs between cost, setup complexity, bandwidth requirements, and latency sensitivity. VPN connections are typically easier and faster to set up, and they work over existing internet connections, but they have lower bandwidth and higher latency. Dedicated connections provide much higher bandwidth and lower, more predictable latency, but they require physical installation and have higher fixed costs. GCP's Network Connectivity Center supports both Cloud VPN and Cloud Interconnect as spoke attachment types. Cloud VPN connections can use either Classic VPN, which is the older, simpler VPN service, or High Availability VPN, which is the recommended option for production workloads. High Availability VPN provides redundant VPN gateways and requires BGP for dynamic routing, which enables automatic failover and route updates. When you attach a VPN connection to NCC, you configure BGP peering between your on-premises router and the Cloud VPN gateway, and the VPN gateway then exchanges routes with the NCC hub. This allows your on-premises networks to learn routes to all the other spokes attached to the hub. Cloud Interconnect attachments work similarly, with BGP sessions established between your on-premises routers and Google's interconnect routers, enabling dynamic route exchange. AWS Transit Gateway provides excellent VPN connectivity through Transit Gateway VPN attachments. These VPN attachments create IPsec tunnels between the transit gateway and your on-premises VPN device, with BGP routing for dynamic route exchange. One of the powerful features of Transit Gateway VPNs is support for equal-cost multipath routing, which allows you to use multiple VPN tunnels in parallel for increased bandwidth and redundancy. Transit Gateway also supports accelerated VPN connections, which use AWS Global Accelerator to optimize the routing path from your location to AWS, reducing latency and jitter. For dedicated connectivity, Transit Gateway integrates with AWS Direct Connect through Direct Connect Gateway, which can connect a single Direct Connect connection to multiple transit gateways across different regions. Azure Virtual WAN site-to-site VPN capabilities are particularly strong, reflecting Microsoft's focus on branch connectivity. Virtual WAN VPN gateways support multiple tunnels per site for redundancy, active-active configurations for high availability, and BGP for dynamic routing. One of the unique features of Virtual WAN is its simplified branch connectivity through SD-WAN partner integrations. You can use configuration files generated by Virtual WAN to automatically configure compatible SD-WAN devices, dramatically reducing the time and complexity of connecting branch offices. For dedicated connectivity, Virtual WAN integrates deeply with Azure Express Route, Microsoft's dedicated connection service. Express Route connections to Virtual WAN hubs support both private peering for access to Azure VNets and Microsoft peering for access to Microsoft 365 and other Microsoft services. Multi-cloud integration strategies. Multi-cloud architectures are increasingly common as organizations seek to avoid vendor lock-in, leverage best-of-breed services from different providers, or meet regulatory requirements that mandate geographic or provider diversity. Implementing hub and spoke networking across multiple cloud providers presents unique challenges because each provider's network operates independently with its own addressing, routing, and connectivity models. The question becomes, how do you efficiently connect resources in different clouds while maintaining centralized control and avoiding the complexity of full mesh VPN connections between cloud providers? GCP's Network Connectivity Center was designed with multi-cloud connectivity as a first-class use case. The router appliance spoke type is particularly powerful for multi-cloud scenarios. You can deploy third-party routing appliances or SD-WAN platforms in GCP, connect them to NCC as router appliance spokes, and then establish connectivity from these appliances to other cloud providers. The appliances can run BGP with NCC to exchange routes, and they can establish encrypted tunnels to resources in AWS, Azure, or other clouds. This gives you a central hub in GCP that can route traffic between your GCP resources, your on-premises infrastructure, and your resources in other clouds. The key advantage is that NCC provides unified route management and visibility across this diverse environment. AWS Transit Gateway can also serve as a multi-cloud hub, though it requires a slightly different approach. The typical pattern is to deploy VPN or SD-WAN virtual appliances in AWS EC2 instances. Attach these instances to the Transit Gateway through VPC's attachments, and then establish encrypted tunnels from these appliances to other cloud providers. Transit Gateway Connect attachments, which support GRE tunnels, can simplify this architecture by allowing direct GRE connectivity to SD-WAN platforms without requiring intermediate VPCs. The challenge with using Transit Gateway as a multi-cloud hub is managing the routes. You need to configure BGP carefully on your appliances to ensure routes are properly exchanged between Transit Gateway and the other clouds. Azure Virtual WAN's approach to multi-cloud is heavily influenced by its SD-WAN partnerships. Many SD-WAN vendors have built native integrations with Virtual WAN that allow their platforms to automatically configure and manage connectivity between Azure and other clouds. The SD-WAN controller can discover your network resources across multiple clouds, automatically establish tunnels, and manage routing without manual configuration. This automation is particularly valuable in large, dynamic environments where resources are frequently created and destroyed. However, for organizations not using SD-WAN, the multi-cloud story is less streamlined. You would typically deploy network virtual appliances in Azure and manually configure connectivity to other clouds through VPN tunnels. Platform comparison. Key differentiators. Now that we have explored each platform individually, let us compare them directly across several key dimensions to understand which platform might be most suitable for different use cases. It is important to recognize that there is no universally best platform. Each has strengths that align with different organizational requirements, existing infrastructure, and operational preferences. The goal is to understand these trade-offs so you can make informed decisions based on your specific circumstances. One of the most significant differentiators is the global versus regional architecture model. NCC's Global Hub model is a major advantage for organizations with worldwide operations that need to connect resources across many regions. With NCC, you create a single hub and attach spokes from any region, and the routing is handled globally. This simplifies management and provides a unified view of your entire network. Transit Gateway's regional model requires creating separate transit gateways in each region and then peering them together. This adds operational overhead but provides better isolation between regions and aligns with AWS's regional service model. Virtual WAN takes a middle ground with a global virtual WAN resource containing regional hubs, giving you both unified management and regional traffic optimization. Another critical difference is how the platforms handle routing domains and network segmentation. Transit Gateway's explicit route table model provides very granular control. You can create complex routing topologies where different attachments have completely different views of the network. This explicitness is powerful but requires careful planning and configuration. NCC's routing is also flexible but relies more heavily on BGP route filtering to implement segmentation. Virtual WAN's routing intent feature provides the simplest model for common security patterns but may be less flexible for complex custom routing requirements. The choice here depends on your team's networking expertise and how complex your routing requirements are. SD-WAN integration is another area where the platforms differ significantly. Virtual WAN clearly leads in this area with native integrations for many SD-WAN vendors and automated configuration workflows. If you're deploying SD-WAN to connect branch offices, Virtual WAN provides the smoothest experience. NCC's router appliance spoke model provides good SD-WAN integration but requires more manual configuration. Transit Gateway Connect attachments support SD-WAN through GRE tunnels, which works well but lacks the automated configuration features of Virtual WAN. For organizations with significant branch office connectivity requirements, This is an important consideration. Cost models also vary significantly between platforms and deserve careful analysis. Transit Gateway charges per attachment per hour plus data processing fees, which means costs scale with the number of connections and the amount of traffic. NCC's pricing is based on the number of spokes and data transfer volume, with different pricing for different spoke types. Virtual WAN has a base per hub hourly charge plus connection unit charges and data processing fees. The most cost-effective option depends on your specific connectivity pattern. You need to model your expected number of connections, traffic volumes, and bandwidth requirements to accurately compare costs. Transit Gateway Route Table Deep Dive. AWS Transit Gateway Route Tables are one of the most powerful features for implementing sophisticated network segmentation and routing policies within your hub infrastructure. Understanding how to effectively use Transit Gateway Route Tables is essential for building secure, scalable architectures that meet compliance requirements while maintaining operational simplicity. Now let's examine the AWS commands in detail. The first command, AWS EC2 Create Transit Gateway Route Table, creates a new route table within an existing transit gateway. The transit gateway ID parameter TGW beginning with 01 ending with 89 specifies which transit gateway this route table belongs to. The tag specifications parameter allows you to apply tags. We are using resource type equals transit gateway route table and setting a name tag with value production RT for identification. The second command, AWS EC2 Associate Transit Gateway Route Table, associates an attachment with a route table. The transit gateway route table ID parameter TGWRTB beginning with 0 ending with 23 identifies the route table, and transit gateway attachment ID parameter TGW attach beginning with 0D ending with 56 specifies the attachment. This determines which route table the attachment uses for routing decisions. The third command, AWS EC2 Enable Transit Gateway Route Table Propagation, enables route propagation. The transit gateway route table ID parameter TGWRTB0ABC123 specifies which route table receives routes, and the transit gateway attachment ID parameter TGW-attach0VPN789 specifies which attachments routes are propagated. For VPN attachments with BGP, all routes learned via BGP are automatically added. The fourth command, AWS EC2 Create Transit Gateway Route, creates a static route. The destination CIDR block parameter quad 0/0 creates a default route matching all traffic. The transit gateway route table ID parameter TGWRTB beginning with 0 ending with 23 identifies the route table, and transit gateway attachment ID parameter TGW attach beginning with 0s ending with 99 specifies the security VPC attachment as the next hop for inspection. NCC Router Appliance Spoke Patterns. Router appliance spokes in Google Cloud's Network Connectivity Center represent a uniquely flexible approach to extending NCC's capabilities with third-party network functions. This spoke type allows you to deploy network virtual appliances such as SD-WAN controllers, advanced firewalls, or routing platforms, and integrate them directly into your NCC hub as first-class routing participants. Let us examine the GCP commands. The first command, gcloud network connectivity spokes linked router appliance create SD-WAN spoke, creates a router appliance spoke. The SD-WAN spoke parameter is the spoke name. The hub parameter myGlobalHub references the NCC hub. The router appliance parameters appear twice for high availability, specifying 2 instances in different zones. The first router appliance parameter, instance, equals projects, my project, zones, US Central 1A, instances, router 1, which is the full resource path including project ID, zone, and instance name. The IP parameter, IP, which equals 10.1.0.10, specifies the internal IP address. The second router appliance parameter specifies the second instance in Zone US Central 1B for redundancy. The region parameter, US Central 1, indicates where these appliances are deployed. The second command, which is gcloud compute routers create NCC router, creates a cloud router for BGP. The name NCC router is given as the router name. The network parameter, transit VPC, specifies which VPC this router belongs to. The ASN parameter, 64512, sets the BGP autonomous system number in the private range. The region parameter, US Central 1, specifies the deployment region. The third command, gcloud compute routers add BGP peer NCC router, configures BGP peering. The peer name parameter SD-WAN peer labels this session. The peer ASN parameter 65001 specifies the router appliance's ASN. The interface parameter if tunnel 1 references the tunnel interface. The peer IP address parameter 10.1.0.10 is the router appliance's IP address for BGP session establishment. Virtual WAN routing intent configuration. Azure Virtual WAN's routing intent feature represents a significant advancement in simplifying security architecture design by allowing you to declaratively specify your routing and security policies. Instead of manually configuring routes, you declare your intent and Virtual WAN automatically creates the necessary infrastructure. Let's examine the Azure CLI commands. The first command, AZ Network vHub Routing Intent creates a routing intent policy. The resource group parameter myResourceGroup specifies the resource group containing the hub. The vHub name parameter myHub identifies the virtual WAN hub. The name parameter Internet Routing Intent is the policy identifier. This creates the container for routing rules. The second command, AZ Network vHub Routing Intent Rule adds a routing rule. The resource group and vHub name parameters identify the hub. The routing intent name parameter Internet Routing Intent references the policy created earlier. The name parameter Internet Traffic labels this rule. The destination type parameter Internet specifies this applies to Internet-bound traffic. The next hop type parameter Azure Firewall routes matching traffic through Azure Firewall, with Virtual WAN automatically configuring all necessary routes. The third command adds another rule for private traffic. The destination type parameter is private traffic, meaning this applies to RFC 1918 private address ranges, RFC 1918. The next hop type is Azure Firewall, routing all private traffic through the firewall. These two rules together implement comprehensive security inspection where all traffic passes through the firewall. High availability and resilience patterns. High availability and resilience are critical considerations when designing hub and spoke network architectures because the hub becomes a central point through which significant traffic flows. A failure or degradation in hub performance can impact large portions of your infrastructure. In AWS Transit Gateway, high availability is built into the service at multiple levels. Each transit gateway is inherently deployed across multiple availability zones within its region, providing zone-level redundancy automatically. For VPC attachments, best practice is to create the attachment with subnets in multiple availability zones. Google Cloud's Network Connectivity Center takes a different approach based on its global architecture. Because NCC hubs are global constructs rather than regional resources, regional failures have limited impact. For VPN connectivity, GCP's High Availability VPN creates redundant gateways with multiple external IP addresses. Azure Virtual WAN implements high availability through its hub deployment model and built-in redundancy features. Each virtual WAN hub is deployed with built-in zone redundancy in regions that support availability zones. VPN gateways are deployed with multiple instances for redundancy. Security integration and inspection architectures. Integrating security inspection into hub and spoke architectures is a critical requirement. The hub represents an ideal location for centralized security inspection because all inter-spoke traffic flows through the hub. Let's examine the security commands. The AWS command. AWS EC2 create transit gateway route, creates a route directing traffic to the security VPC. The destination CIDR block parameter RFC 1918 matches traffic in this private address space. The transit gateway route table ID parameter TGWRTB spoke identifies the spoke route table. The transit gateway attachment ID parameter TGW attach security VPC routes traffic to the security VPC where firewalls inspect it. The Azure command, AZ network firewall create, deploys Azure firewall in a virtual WAN hub. The name parameter my hub firewall identifies the firewall. The resource group parameter my resource group specifies the resource group. The SKU parameter AZFW hub is critical. This specifies the hub integrated SKU designed for virtual WAN. The vHub parameter myHub specifies the hub. The public IP count parameter 1 assigns one public IP for outbound internet connectivity. The GCP command, gcloud network connectivity spokes linked router appliance create FW spoke, creates a router appliance spoke for a firewall. The FW spoke parameter names the spoke. The hub parameter my hub references the NCC hub. The router appliance parameter specifies the compute engine instance running firewall software that supports IP forwarding and BGP. SD-WAN integration and branch connectivity. SD-WAN technology has revolutionized how organizations connect branch offices and remote sites. Integrating SD-WAN with Cloud Hub and Spoke architectures enables a unified WAN that seamlessly extends from branch offices to cloud resources. Let's examine the SD-WAN commands. The first AWS command. AWS EC2 create transit gateway connect, creates a connect attachment for GRE-based connectivity. The transport transit gateway attachment ID parameter TGW attach VPC specifies an existing VPC attachment that serves as transport. The options parameter protocol equals GRE specifies GRE protocol for tunnels. The second AWS command, AWS EC2 create transit gateway connect peer, creates a connect peer representing the SD-WAN endpoint. The transit gateway attachment ID parameter, TGW attach connect, references the connect attachment. The peer address parameter, 10.0.1.10, is the SD-WAN appliance's IP address. The inside CIDR blocks parameter, 169.254.100.0/29, specifies linked local addresses for BGP peering. The BGP options parameter, peer ASN equals 65,000, configures the SD-WAN appliance's BGP ASN. The Azure command, AZ network VPN site create, creates a VPN site representing a branch office. The name parameter branch office 1 identifies the site. The resource group parameter my resource group specifies the resource group. The virtual WAN parameter my vWAN associates with the virtual WAN. The IP address parameter 203.0.113.10 is the branch's public IP. The device vendor and device model parameters specify Cisco Meraki, enabling vendor-specific configuration files. The link speed parameter 100 indicates bandwidth in megabits per second. Performance characteristics and bandwidth limits. Understanding the performance characteristics and bandwidth limits of each hub and spoke platform is crucial for capacity planning. Performance involves throughput, latency, packet processing capacity, and connection limits. AWS Transit Gateway provides impressive throughput with support for up to 50 gigabits per second per VPC attachment. The aggregate bandwidth across all attachments is theoretically unlimited from the transit gateway perspective. For VPN attachments, each tunnel supports up to 1.25 gigabits per second. Google Cloud's Network Connectivity Center leverages Google's global network backbone. VPC spokes can utilize the full bandwidth of Google's network. VPN spokes using high availability VPN support up to 3 gigabits per second per tunnel. Cloud interconnect spokes support from 10 to 200 gigabits per second. Azure Virtual WAN's performance is defined by the hub's scale unit configuration. The minimum configuration provides up to 2 gigabits per second of VPN throughput and 20 gigabits per second of ExpressRoute throughput. Maximum configurations support up to 20 gigabits per second VPN and 100 gigabits per second ExpressRoute. Cost optimization strategies. Cost management is critical when operating hub and spoke architectures at scale because costs accumulate from hub infrastructure charges, per attachment fees, data processing charges, and data transfer charges. Let's examine the cost monitoring commands. The AWS command, AWS CloudWatch Put Metric Alarm, creates a CloudWatch alarm monitoring transit gateway costs. The alarm name parameter TGW data processing alert identifies the alarm. The alarm description provides documentation. The metric name parameter data processing tracks traffic volume. The namespace parameter AWS/transit gateway indicates transit gateway metrics. The statistic parameter sum totals data over the period. The period parameter 3600 specifies 1 hour in seconds. The evaluation periods parameter 1 means threshold must be exceeded in 1 period. The threshold parameter is 1 terabyte in bytes. The comparison operator parameter greater than threshold defines the trigger condition. The Azure command, AZ consumption budget creates a budget for tracking spending. The budget name parameter, VWAN monthly budget, identifies the budget. The amount parameter, 5000, sets the budget limit in your billing currency. The time grain parameter, monthly, specifies a monthly budget. The time period parameter, start date, equals 2024-01-01, indicates when tracking begins. You would configure alert rules separately to notify when spending approaches thresholds. Operational management and monitoring. Operating a production hub and spoke architecture requires comprehensive monitoring, troubleshooting capabilities, and operational tools that provide visibility into network performance, connectivity status, and routing behavior. Let's examine the operational commands. The AWS command, AWS logs filter log events, queries transit gateway flow logs. The log group name parameter /AWS/transit gateway/flow logs specifies the log location. The filter pattern parameter searches for specific traffic. For example, source add_r equals 10.0.** matches source addresses in RFC 1918, and action equals reject filters for rejected traffic. The start time parameter uses a shell command to calculate 1 hour ago in Unix timestamp milliseconds. The GCP command gcloud alpha monitoring policies creates an alerting policy. The notification channels parameter specifies where alerts are sent using the full resource path. The display name parameter NCC spoke down alert provides a readable name. The condition display name parameter spoke unhealthy labels the condition. The condition expression parameter monitors NCC spoke state metric, alerting when value equals 0, indicating the spoke is down. The Azure command, AZ network watcher connection monitor creates a connection monitor for active testing. The name parameter VWAN connection monitor identifies the monitor. The location parameter East US specifies where monitoring runs. The endpoint parameters define source equals VNet 1 virtual machine and destination equals VNet 2 virtual machine. The test configuration parameters define protocol equals TCP on port equals 443, with threshold equals 50 milliseconds for latency alerts. Migration strategies and best practices. Migrating to hub and spoke topologies requires careful planning to avoid disrupting production services. Network migrations are inherently risky because network connectivity is fundamental to all services. Let's examine the migration commands. The first AWS command, AWS EC2, describe route tables, retrieves route table configuration. The filters parameter with name equals VPC ID and values equals VPC migrated limits output to the migrated VPC's route tables, verifying routes point to transit gateway. The ping and traceroute commands test connectivity. Ping sends ICMP echo requests to test basic connectivity. Traceroute shows the network path packets take, revealing if traffic goes through transit gateway as expected. The AWS EC2 describe transit gateway attachments command lists attachments. The filters parameter with name equals state and values equals available shows operational attachments, confirming the migrated VPC attachment is ready. The AWS CloudWatch get metric statistics command retrieves traffic metrics. The namespace parameter AWS/transit gateway specifies transit gateway metrics. The metric name parameter bytes in shows traffic flowing into transit gateway. The dimensions parameter filters to a specific transit gateway. The start time and end time parameters define a 24-hour window. The period parameter 3600 aggregates into hourly buckets. The statistics parameter sum totals bytes transferred. The rollback commands show quick reversion. The AWS EC2 delete route command removes the transit gateway route. The route table ID parameter RTBXYZ identifies the route table. The destination CIDR block parameter 10.2.0.0/16 identifies which route to delete. The AWS EC2 create route command restores the VPC peering route with VPC peering connection ID parameter PCXABC specifying the peering connection. Thank you for your attendance. Please consider subscribing to the channel.